Hello everybody! Today I'm going to be teaching how to do another physics problem, but today this is from, again, 1984, but this time it's the second mechanics problem, alright? I will show you the picture, I'll read it to you, and I have my own diagram, as usual, okay? Alright, let's start. Two satellites of masses m and 3m, respectively, are in the same circular orbit about the Earth's center, as shown in the diagram above. The Earth has mass me and radius re. In this orbit, which has a radius of 2 re, the satellites initially move with the same orbital speed v initial, but in opposite directions. Okay? So this is the diagram. I don't know if you can see. Hold on. I'm sorry. Okay. There we go. So I have my own diagram in case that wasn't too well. So it's just a lot bigger. Okay? Alright. So for A, they want us to calculate the orbital speed of the satellites in terms of g, the mass of the Earth, and the radius of the Earth, okay? Alright, so let's start with the sum of the forces. It's always something reliable to go to. Okay, so the sum of the forces is going to be equal to the mass times the centripetal acceleration, okay? Because the force is the centripetal force, which is going to be equal to mv, in our case, v squared over r. But the centripetal force itself is the force of gravity. And so the force of gravity is going to be equal to g times the mass of the Earth times the mass of the object over r squared, which is the radius of the Earth, okay? So you're going to set the force of gravity equal to the centripetal force, and basically we're just going to solve for v, okay? Alright, so let's set this equal. Alright, so since we have masses on both sides, we can cancel them out, and we have at least one radius in the denominator of both sides, so we can cancel that out. So we have that, and so now when we solve for v, it's basically just algebra. So you're going to get v is going to be equal to g, which is a gravitational constant, times the mass of the Earth itself, divided by 2 times the radii of Earth. Because you have to remember that the radius here is going to be equal to 2 of Earth's radii, okay? Alright, so that's A. We calculated the velocity initial, okay? Alright, so now B. Assume that the satellites collide head-on and stick together. In terms of v, find the speed v in the combination immediately after the collision. Alright, so the first thing that we should pop to is the conservation of linear momentum. So the initial momentum is going to be equal to the final momentum. Alright, that's how we should start. So the initial momentum is going to be the sum of all the individual momentums of each object moving before the collision. So it's going to be 3m times v, which is going to be up here, that's the sky, minus, normally be plus because it's a sum of, but because they're moving in opposite directions, you're going to take the difference, okay? So it's going to be minus just m times v. So this is going to be the total initial momentum. You're going to set that equal to the final momentum. Because they stick together, you're going to add that. So you're just going to get 4m, but this is v final because that's what we're searching for. So basically that's our equation right there. And we can cancel out all the m's because they're going to be constant on both sides. So m cancel. So you're going to have 2v is going to be equal to 4vf. Alright? So when you solve for vf, you're going to get vf is equal to 1/2 of v. So basically, both satellites moving together are going to be moving at half the speeds that they were individually, okay? Sounds good? Alright, now let's move on to part 3. Or C, sorry. Okay. Assume that the gravitational potential energy of an object is defined to be 0 at an infinite distance from the Earth. Okay, so, Calculate the total mechanical energy of the system immediately after the collision in terms of G, little m, which is the mass of the satellites, the mass of the Earth, and the radius. Alright, so basically they want us to use the conservation of energy. So the total energy is going to be equal to the kinetic energy of the system plus the potential energy of the system. Basic rule, okay? And by definition, we know that the kinetic energy is going to be equal to 1/2 mv squared. So we have our 1/2. And this is because it's after the system, so the mass of both satellites is going to be equal to 4m, because we figured that out earlier. And the final velocity is something we found out earlier, so it's going to be 1/2 v squared, because they want it in terms of v. You're going to have 1/2 v squared. Alright, so that itself is going to be the kinetic energy. And now we need potential energy. So the potential energy is equal to, it's the formula that's minus G mass times the Earth times mass of the object divided by the separation distance, okay? So it's going to be minus the gravitational constant times the mass of the Earth times 4m, again, which is the mass of both satellites stuck together, divided by 2 of Earth's radius, which is this distance, okay? Sorry. Okay, so basically when you do that out, you're going to get 1/2 m times GME over 2RE minus GM times 4m over 2RE. So again, you can simplify that farther and make it prettier than that, because that's a lot to deal with. And so it's going to be equal to -7 G m of the Earth times the m of satellite over 4 times Earth's radius, okay? And that itself is the total mechanical energy of the system right after the collision, alright? We finished A, B, and C, so that means we're it. Okay, so I guess that's it. Thanks for watching, and have a great day. Bye.